Swayam Prabha. Digital India. Educated India.
So essentially this is going to be a workout session. We look at solutions, okay, to the questions. So let me show you the questions. So here is the first one. So one is asked to look at this curve, which is so you have this function, y equal to sine x, okay. So you have this, so here's the first question. You have the plane curve given by the graph of the function y equal to sine x, okay, taken from minus pi to plus pi, okay. And there are 5 parts to this question. Find the unsigned curvature, the formula for the unsigned curvature. That means it should, so at the point corresponding to x, so on the graph of the curve it's the point x comma sine x. So you need the curvature as a function of x, okay. So that is the first one. That is just a matter of applying the formula. So if you take y equal to sine x, y equal to sine x, okay, then so this is a graph of y equal to sine x, and of course this is a sine graph. It's from, you are taking it from minus pi to pi, okay, and therefore you are going to get this portion is a sine curve, all right. And we want the curvature, so we want the unsigned curvature function, and this is given by kappa of x. So you see, if you take a curve parameterized by gamma t, then the curvature function, the unsigned function kappa t is given by norm of gamma dot cross gamma double dot by norm gamma dot cube, okay, and where this gamma dot is supposed to be d gamma by dt, okay. This is if the parameterization is done by t, okay, but in this case the parameterization is done by x. So first of all you have to be clear about what is the parameterization. It is gamma x here, and the parameterization is x comma sine x, okay. So usually this gamma t will have it will have two components. It is written as x of t and y of t, okay. And in this case you see the instead of t you have x, okay, and the gamma x is x comma sine x, okay. So you have to make this calculation. If you do it in general for a function, you could have done it for a function x comma fx, for a function y equal to fx, and the graph is the points in the graph are x comma fx, okay. So in this case fx is sine x, okay, and we have already checked this. The curvature function is mod f double dash of x divided by square root of 1 plus f dash of x squared whole cube, okay. So this is what it is, which directly comes from this formula, all right. So in this case the function is sine x, second derivative, first derivative is cos, second derivative is minus sine. So you will get, basically you will get sine x, and I want unsigned curvature, so I have to put a mod, all right, and of course I will get divided by 1 plus cos squared x to the power of 3 by 2. So this is the curvature function. So yeah, sometimes I am using kappa and sometimes I am using k. So let me just stick to k, which is easier. So I'll put the thing on the right as k, right. So this is the curvature function, all right, And so this is the first part of the question. Then yeah, so the mod in the sin x is important, all right. So for people who have missed the mod, I have cut half mark, okay, because I have specifically mentioned that it is unsigned curvature. And the reason is because if you don't put the mod and you just keep it as sin x, then there is a likely confusion will come, namely from you see from the graph, you see of course sine is negative from minus pi to 0, okay, and what will happen is that it will look as if the curvature is negative, all right, but actually the truth is the curvature is positive, and this is wrong, okay. So it's the putting the mod is very, very important, all right. And that is also another part of the question, okay. So this putting mod is a very, very important thing. This is supposed to carry 2 marks, okay, and for this formula, all right, you just have to directly apply the formula. Half a mark is reduced if the mod is not there, okay, because the mod is essential. So then we have the here is the next question, the next part of the question. So this question has 5 parts, and 10 marks are given to it. So each part is about 2 marks, all right, and the estimated time for this is about 15-20 minutes, okay. This is a direct question. So the next question is find the maximum and minimum unsigned curvatures and the points where these curvatures are attained, okay. So for that, so let me write that down. So part 2, finding finding maximum and minimum curvatures and the points where they are attained. Okay, so so basically you have this function, and of course when I say maximum and minimum curvatures, these are unsigned curvatures. That's very, very important, okay. So let me stress it's unsigned curvature, unsigned, okay, because if you take the sign, negative values will come in and change the minimum, all right. So so you have to look at this function kx is mod sin x by 1 plus cos squared x to the power of 3 by 2. And I mean in this case, of course you can use calculus to find maxima and minima, okay, but you don't have to really do that, because you see if you look at the functions involved, okay, it's clear that for this to be a maximum, okay, you want the numerator has to be the maximum, a maximum, and the denominator has to be a minimum, and it happens, okay. So you are only looking at the portion of the graph from minus, so I think I have given minus pi to pi, open interval. That means I am not including minus pi and plus pi, okay. So you should forget this point and you should forget this point, it's only in between, okay. And so if you look at it, you can see that this maximum is attained, the mod sine, so it's the numerator. You see the denominator, there is a 1 there, okay, and no matter what cos squared x is, cos squared is bounded anyway from minus, cos squared is going to be bounded from 0 to 1, okay. So this 1 is important because this is actually the velocity, this is the velocity vector. So gamma dot x, which is actually so gamma x is just x comma sin x, okay, and gamma dot x is 1 comma cos x, and norm gamma dot x, okay, here you see the dot is actually d by dx, okay. So norm gamma dot x will be this square root of 1 plus cos squared x, and this is always greater than 0, okay. So this is a regular parameterization, okay. The graph of any curve is always a regular parameterization because the first coordinate will be the parameter, okay, and its derivative will be 1, and the velocity will never vanish, okay. So this denominator is not going to create a problem, okay. It's the numerator that you see, the numerator at x equal to 0, it's going to be 0, all right, and that is the minimum value you can get, and the maximum value will come at x equal to when sin x is 1, okay, and then of course cos x is 0. So basically what will happen is that, at x equal to 0 you will have maximum k x, that will be I mean minimum k x will be 0, it will be 0, okay, and when x equal to so if you want the numerator to be the maximum, x should be plus or minus pi by 2, okay. So I will put plus or minus pi by 2, you will get the maximum curvature as 1, and mind you, it's unsigned curvature, okay. If you hadn't put the sign, you will get a minus 1 plus 1, okay. So so this is again, this is again 2 marks for finding the points and the points of maximum minimum curvature and finding the corresponding curvatures, okay. So so that is this part of the question. Then let's look at the third one. So at the points of maximum and minimum curvature, we want the center of curvature and the radius of curvature, all right. So this is again rather straightforward, except that, to find the center of curvature, there is we have derived a formula for the coordinates of the center of curvature, okay, and basically that formula involves the sine normal and the sine curvature, okay. Computing that formula by itself is a little cumbersome, okay. So some people do it, but that is not necessary. The idea is that if you know physically where the geometric normal is pointing, okay, from the point on the curve, then you travel a distance along that direction which is equal to the radius of curvature, and the radius of curvature is reciprocal of the curvature, and then you can easily find the center, okay. So what happens, so that is the easiest way to do it. So in this case, what is going to happen is you are going to have, so let me write that down, finding the curvature, the radius of curvature, the center and the radius of curvature, the centers and radii of curvature at the points of maximum and minimum curvature, and of course I should keep stressing it is unsigned, okay. So so you have already, so if I draw this picture again, okay, so this is minus pi, this is 0, this is pi, so you already have these 3 points. One at 0, what happens is that the curvature is 0, okay, and curvature is 0 means, it should be a straight line. So basically what happens is that, the circle of curvature is going to be a straight line, okay. The radius of curvature will be infinity, okay. So k is 0 implies radius of curvature is plus infinity, okay, and we should think of so it should be a circle passing through that point with infinite radius, okay. So basically it should be thought of as a straight line, okay, and remember that this straight line will have you can think of infinity as the center of curvature, okay. And there is a small bit of a confusion, where is infinity, what is a single point that you can call as infinity on the plane, okay. So infinity is in all directions, okay. So here is where actually some projective geometry helps, okay. You in topology, this is what is called as one-point compactification. That is, you take you put a single point, you add a single point to a space, and then you make it compact, okay. And so I just want to say this because you need to understand this point at infinity. This is somewhat of a confusion. If you use formulas and try to compute it, okay, what will happen is that you will get the center of curvature with the coordinates, x coordinate you will get plus or minus infinity, y coordinate you will get plus or minus infinity, okay. So you can get something like that if you really make a computation, but you must understand that such a computation is not valid, because infinity, you cannot have a point with coordinates, one of the coordinates even being infinity. Okay, that point is kind of and if you look at it in a pictorial kind of way, you see infinity is the point. Infinity can be approached in so many directions. Okay, so it appears that there are so many infinities. Okay, in a way that is also correct. Okay, but if you go to projective geometry, there is something called a line at infinity. Okay, but what we are doing is that we want to have a single point at infinity. This is a different concept, and this point at infinity corresponds to this one point at infinity in the complex plane. Okay, which is called the extended complex plane if you do complex analysis. So the way to do it is what is called the stereographic projection. So I just want you to understand that you see, let me draw a picture. See, if you take the whole real line, okay, normally if you take the whole real line, then this is written as minus infinity plus infinity. Your real line is minus infinity to infinity. Okay, and the truth is that you think of plus infinity as a point lying in this end, at the end, if there is an end. Okay, and minus infinity is on this end. Okay, and the point, and they are two different points. Basically, they are two different directions. Okay, what we do is that we put them together and make them into a real point and call it as one. We add one point at infinity, and then this is what is called a one-point compactification. All right, and the advantage of this is that you can think of a limit of any real variable as the modulus of the variable approaches infinity. If the modulus of a real variable approaches infinity, the real variable can either approach plus infinity or minus infinity. Okay, you want to get that make sense of that statement, and the way to do it is the stereographic projection. So what you do is that basically, so you put this line as the x-axis. Okay, and then you take the y-axis, and what you do is that you draw a circle here. Okay. This is a circle, let us say, of radius 1, centered at so this point is 1, 0. Okay, I'm sorry, rather 0, 1. Okay, so you take this point which is 0, 1, and then this point is 0, 2. Okay, and this is circle of radius 1. Now what you do is this point here above, this is the point at infinity. It's called the point at infinity, and this, what you do is you do the following thing. You do what is called as the Riemann Stereographic projection. So the correct version is only for the plane, but this is the motivating case on the real line. So what happens is that you are going to do the following thing. See, for every point on the real line, okay, what you do is you simply join this point to this topmost point on the circle, which if you want, call it as the north pole. Okay, and then you get this point p prime on the circle. Okay, so you have this the advantage of this is that you get a map from R to to the circle. Okay, and which sends p to p prime. Okay, and the beautiful thing about this map is this map is continuous. This is 1, 1 or injective, and this is continuous. Okay, and here is the beautiful thing about this map. What it will do is that as of course, if I taken a point, let us say P1 on the right side, okay, then I will get the corresponding point P1 dash on the other side. Okay, and as you see, you take either the point P and make it go to minus infinity, or you take the point P1 and make it go to plus infinity. You will see that the point P, as P goes to minus infinity, you will see that this point P1 goes like this and tries to approach the point at infinity. Okay, and as P1 goes to infinity, you see the P1 dash also goes and tries to approach the same point. So what happens is that both plus infinity and minus infinity, they correspond to the same point, and it's a real point that you can work with. Okay, so we say that the circle is the one-point compactification of the real line. Okay, and the word compactification also has a topological meaning. It is compact in the sense of topology, which is that every open cover has a finite subcover. But the real line is not compact. It is not, because it is not bounded. Okay, so there is a theorem called the Heine-Borel theorem in topology, which says that a subset of Euclidean space is compact different only if it's both closed and bounded. Okay, closed means it has to contain its boundary points or limit points, and bounded means that it should be contained in a finite ball centered at the origin. Okay, that is the distances of any pair of points in that set that should have an upper bound. It should not be unbounded. You should not be able to find points in the set which are at arbitrarily large distances from each other. Okay, so it's bounded in the real physical sense. Okay, so the so-called Heine-Borel theorem in topology says that a subset of Euclidean space, n-dimensional real space, is compact different only if it's both closed and bounded. So if you have an unbounded set, then it's not going to be compact. The real line is an unbounded set, so it's not compact. So the idea is that after adding this point at infinity, the real line becomes a circle, and the circle is compact. It's both closed and bounded. Okay, so it's called the one-point compactification. So you can think of the point at infinity like that. Now what you can do is, this is the real line case. You can do this also to the plane, which is what we want. So what happens is that in the case of the plane, you do the following thing. So here is your plane. So I am drawing it, trying to draw a three-dimensional picture. So this is my x-axis, this is my y-axis. Okay, and this is the whole plane. You see the plane again is unbounded. Okay, you can always find pairs of points whose distance is as large as you want. So the plane is unbounded. All right. So it's not compact in that sense, in the topological sense. But again, you can add a single point at infinity for the plane. So what you have to do is, in the one-dimensional case, you put a circle. In the two-dimensional case, you have to put a sphere. So basically, what you do is that you take this z-axis, okay, and you draw a sphere here. Okay, the same way. Okay, and now this sphere is again centered, if you want, centered at this point on the z-axis. So it will be x equal to 0, y equal to 0, z equal to 1. Okay, and this is the so-called north pole. This is going to be x equal to 0, y is equal to 0, z is equal to 2. Okay, and mind you, this is a sphere, so I will just put something like this. Okay, it's not a circle. Okay, it's a sphere sitting on top of the origin. All right, radius 1. All right. Now again, you do the same business. What you do is that you take a point on the plane P. Okay, then this so-called point on the sphere, which is 0, 0, 2, is called the north pole. If you think of the sphere as the Earth, then that is the north pole, and the origin is the south pole, if you want. Okay, now what you do is that you join this P to the sphere. Okay, and it will hit the sphere exactly at one point, and that is your projection. So that's the point P prime. So what happens is that from R2, which is the plane, okay, you have a map into the sphere, and that is again the map P going to P prime. Okay, and again this map is both one-to-one and continuous. And here is a beautiful thing. You can make sense of the point P going to infinity. And the way you say a point goes to infinity is by saying that its distance from the origin goes to infinity. Okay, so here also on the real line, you can say the point P goes to infinity by saying its distance from the origin goes to infinity, which means, in principle, it means that it can either go to minus infinity or plus infinity, as we understand it. But you are only looking at the mod, and that is the distance. All right. So in the same way, what you do is, we say P tends to infinity on the plane if the distance of P from the origin, that goes to infinity. Okay. So the advantage of this is that if P goes to infinity in any way, so the P can go to infinity in an infinitude of directions. But as P goes to infinity in any direction, okay, what will happen is that this P prime will approach the north pole. Okay, and the beautiful thing is that there is this idea of a neighborhood of infinity, okay, which is very, very important for topology and complex analysis. The neighborhood of infinity is actually neighborhood of the north pole, because you see, if you look at it by this projection, you will see that I can on the north pole, this is the north pole, a neighborhood will be, so let me use a different color. So the neighborhood will be something like this. It will be like a small cap surrounding the north pole, and I can make the size of this cap as small as I want. Okay, I can make that size very, very small. I can shrink it. But what will this correspond to on the projection? What it will correspond to on the projection is, if you look at it, you will get the exterior of a large circle in the complex plane. That's what you will get if you imagine it. Okay. So the neighborhoods of infinity on the sphere, on the north pole of the sphere, which is the point at infinity, they are all like exteriors of large circles in the plane. And a point in the exterior of on the exterior of a large circle in the plane is a point closer to infinity. And as the larger the circle, the exterior is closer to infinity. You understand? So that's what is happening. So what I want to tell you is that this is called the Riemann Stereographic projection. This is how you add one point to the plane. Again, the point is, when you add this one point to the plane, it becomes compact. The plane is unbounded, so it's not compact. But you add this one point, it becomes a sphere, and a sphere is compact. Okay. So what I want to say is that in this case, you see at the origin. So this is the graph of y equal to sine x. Okay. Then at the origin, what happens is the radius of curvature is infinity. The center of curvature, if you want to really geometrically define it, it should be the point at infinity, and there is only one point at infinity. And how do you make sense of one point at infinity? It's using the stereographic projection, as I told you. Okay. So what happens is that if you draw the circle of curvature, it will be a straight line. This is the circle of curvature at 0. Okay. And the center of curvature will be at 0 will be the point at infinity. Okay. So where this point at infinity has to be understood in the sense of the stereographic projection. Okay. And but of course, you can say that the center of curvature lies at infinity. I'm fine with that. Okay. But then the question is, where is this infinity? I mean, is it a single point? If you want to really see it as a single point, and the answer is, you have to use this topological Riemann stereographic projection to understand a single point at infinity. Okay. So this is at the situation at 0. Okay. What about, so where 0 is of course the minimum, at x equal to 0, the minimum curvature is 0. Okay. What about points of maximum curvature? Okay. So you have a question? You mean the circle, the circle of the sphere? Yeah. So some books usually use center at the origin. Okay. But the problem is that if you use center at the origin, what will happen is that the unit disk will get projected to the lower hemisphere. Okay. And I didn't want to, I could have done that also. See, even in the real line case, I could have used circle centered at the origin. What will happen is that the unit interval -1 to 1, that will get projected to the lower semicircle. Okay. And that makes it a little bit confusing. So that is the reason I translated it by 1 unit. Okay. But you can use either. Okay. Basically, it's a projection of a straight line onto a circle. All right, with respect to a point on the circle. All right, that's what it is. Right. So let me get back. We want to understand what happens to the circle of curvature. I mean the center of curvature, radius of curvature at the points of maximum curvature. So you see, for example, you take this point. So that is this point, which is, so let me try to use a different color. So you see, or rather, so you see, let's take this point. This point is x coordinate is -π/2. Y coordinate is also is -1. Okay, this is the point. And at this point, you see, look at it. The curvature is maximum. The curvature is 1. Okay, and mind you, it is unsigned curvature. All right, and therefore the radius of curvature is the reciprocal of that. That is also 1. So that means that the center of curvature lies from this point at a distance of 1, but it should be in the direction of the geometric normal. Okay, and the geometric normal will be like this. Okay, so it will be like this. Okay, and so basically you will get this point which is minus pi by 2 comma 0. This is the center of curvature. Okay, so for x equal to minus pi by 2, radius of curvature is 1, center of curvature is minus pi by 2 comma 0. Okay, and if you are a little careless about the sign, you could end up with minus pi by 2 comma minus 2 or something like that. Okay, so you have to be careful. Think always geometrically. All right, making actual computations using the vector formula of the evolute is always somewhat confusing. Okay, then there is the other point where you have maximum curvature, and that is, so you see here, what I want you to understand is, see, this is circle, mind you, centered at minus pi by 2 0, radius 1. So what will happen is, the circle of curvature will look like this. So this will be a circle of curvature. It will be radius 1, and centered at minus pi by 2 comma 0. Okay, so let me write this. Okay, so this is a circle, and then by symmetry you can expect that the same kind of thing will happen here at the point corresponding to x equal to pi by 2, y equal to 1. Okay, the geometric normal will point like this. The curvature is 1, which is the maximum. Radius of curvature is reciprocal of that is 1. Okay, and you are going to have the circle here. Okay, you are going to have the circle here. Okay, and this point, of course, the center will now be pi by 2 comma 0. Okay, so the centers of curvature are plus or minus pi by 2 0, and the radii of curvature are 1. All right, what is happening is only at the point x equal to 0, this you get a straight line. Okay, and this straight line is thought of as circle of curvature with center at the point at infinity. Okay, and radius is also infinite. Okay, so that is this part of the question. So here is the next part of the question. What happens to the circle of curvature as x changes from minus pi by 2 to pi by 2? And so I wanted a geometric interpretation of that. Okay, which means that you should look at it pictorially. Okay, so as you can guess, this is what is happening. So the picture is like this. What happens to the circle of curvature at so the question was as x varies from minus pi by 2 to pi by 2. Okay, so from this picture, so you see here is the curve, right, and you see at this point you have maximum curvature. The circle is like this. Okay, now if you go to and at the origin you have the straight line. Okay, and then here again you have the circle of curvature like this, right, and in between what is happening is that you see the curvature here is maximum, and at the origin it is 0, so that means it is decreasing, and the radius of curvature is therefore increasing. So that means these circles are becoming larger and larger. So basically what will happen is that as you can expect, you are going to get bigger and bigger circles. So these circles are going to become larger and larger. Okay, and you see these larger and larger circles, finally they kind of degenerate to this line. Okay, and then at just exactly beyond that line, the circles are going to flip to the other side. So what's going to happen is that you're going to get things like this. Okay, and then you're going to get probably bigger and bigger circles, and then finally it's going to the smallest you are going to get is at pi by 2. Okay, so it's going to be like, it's going to look like this. So basically what is happening is that these circles starting at minus pi by 2 to as you go, the circles are becoming larger, they degenerate to this line, and then they flip over to the other side, and they again shrink. So this is what is happening. What is important is that the circles degenerating to a line at the origin is what is very, very important. That is the most important part. Okay, this, and there seems to be a flipping. Now I want to say something about this. This flipping is suddenly, it looks like as if the centers of curvature have changed. They have crossed from one side of the line to the other side. Okay, and of course so what it looks somewhat discontinuous if you look at it like that, because on this side, if you look at in this direction, see, if you look at this direction, on this side, it looks like the centers of curvature are going to the infinity in the second quadrant, if you want, whereas on this side, the centers of curvature are going to the infinity in the fourth quadrant, if you want to think of it. So it looks like at 0, it's like there is a sudden flip from the second quadrant to the fourth quadrant. It looks very discontinuous. Okay, but don't look at it like that. That's because you are separating the infinity being approached from the second quadrant to the infinity being approached from the fourth quadrant. Think of the only one point at infinity on the Riemann sphere. Then what happens is that this is a continuous operation. What is happening is that it is the same point at infinity no matter how you approach it. So from that sense, it's actually continuous. So what is happening is that the point at infinity there or in any direction is the same in that identification. So it's not a discontinuous thing. That's what I want you to understand from the sense of the stereographic projection. Okay, so the important thing is that these circles become larger, they degenerate to a line, and then they shrink again. All right, and what is actually happening? Why is this flipping happening? What is the significance of this flipping? Is because you see the sign of curvature is changing, which is actually the next question. Okay, and which is the last part of the question. See, it's very important to look at what are this part of the question, namely what are the points of positive and negative curvature. Okay, so here is where something you have to worry about it. So you see, remember our so let me write this. See, points of positive and negative curvature. So when I say points of positive and negative curvature, what I mean is here it is, of course, I mean sine curvature. So this is very, very important. The moment you start putting plus, when you talk about sine of a curvature, it must be only sine curvature. Okay, and the idea is very, very simple. You have to look at it geometrically. If the geometric normal is in the direction of the sine normal, the curvature is positive. If the geometric normal is opposite to the sine normal, the curvature is negative. And now look at it. If you look at the curve like this, okay, you see when you are on this arm of the curve, which is from minus pi to 0, okay, this is the tangent, assuming that you are moving the curve like this. This is the tangent. The sine normal will be like this. Okay, so this is the gamma dot, and this is the ns, the sine normal. Okay, and you see the sine normal is actually pointing in the right direction. Okay, the circle of curvature is above. The center of curvature is above. So what happens is from here to here you will have positive curvature. Okay, and then if you take any points here, you see now that the gamma dot will be, the tangent direction will be like this. The sine normal will now be like this. So the sine normal is obtained by taking the tangent and rotating it by 90 degrees anti-clockwise. So this will be the sine normal. Okay, now you see, but the curvature the curvature will be along this direction. So what happens is the curvature direction is to be taken from the point to the center of curvature. That is a geometric normal. So that is in the opposite direction. So what happens is from here to here it is negative curvature. Okay, and therefore these are the regions. But if you look at the formula and don't take the sign, okay, if you look at the formula and don't take the sign, it will be very misleading. See, because remember our curvature formula was kx equal to, it was mod sin x by root of 1 plus cos squared x to the 3 to the power of 3. Okay, so you can think of it like this. If you take kx as minus sin x by root of 1 plus cos squared x to the 3 by 2, if you take it like this, then everything works all right. But the point is that this minus sign, is that the correct thing to put? Because the formula for kx, it's norm. Numerator you have norm of gamma dot cross gamma double dot. Denominator you have, of course, again norm of gamma dot cube. So what sign to put is always, you have to worry about it. So if you don't put the sign, okay, then you are in trouble. What happens is that if you write mod sin x divided by this, and you forget to put the sign, then sign is negative here, so you will get a negative sign here where you have to get a positive sign, and you get a positive sign here where you will get a negative sign. So you can go wrong. All right, so that is one thing. Then I just wanted to so the thumb rule is always look at the direction of the geometric normal and look at the direction of the sine normal. If they are in the same direction, curvature is positive, the sine curvature is positive. If they are in opposite directions, the sine curvature is negative. That's how you have to see it. Okay, I plotted a few of these for you so that I can show you. So you see, this is the curvature. Okay, y equal to mod sin x by 1 plus cos squared x to the 3 by 2. I am using the GeoGebra suite, which is actually free. Everybody can use it. So you see, if you look at it, this is the curvature function. Okay, and you can see that it kind of goes to maximum 1, minimum 0. Okay, but if you look at it very carefully, you see the sine curvature function is not smooth. At the origin, you see it's like the mod function, which is not smooth because you have two tangents. Okay, but here is the interesting thing. If you had not put the mod, okay, then the sine curvature function is smooth. Okay, so that is something that you can see. All right, so you can always graph these things. Okay, okay, so I think I'll have to continue in the next lecture. I have to discuss the other questions. All right, so we will stop here for the moment.